Now we're going to learn how to compute and interpret probabilities. We're going to look at two methods, the empirical method and the classical method. Now with the empirical method, we do not know the probability of a certain event. We'll call it E. We can conduct a series of experiments to approximate it by the number of frequencies that we see event E occurring in proportion to the total number of trials that we do. And so it becomes just a division problem. So the probability of that event E is approximately the frequency that we see E, the number of times we see that event, that is, divided by the total number of trials. And this does become a good approximation to the probability of that whatever event we're looking at if we have a large number of trials, the law of large numbers. So let's look at an example. We wish to determine the proportion of students at a certain school who have AB blood. So we look at 100 students and we find out what their blood type is. We find out, so our event is those students that have AB blood. So we see that 3 of those students have AB blood. So the number of times that we see the event we're looking for, people with AB blood, was 3. So using the empirical method, we would say that the number of ways we saw event E, people having AB blood, was 3 divided by the number of times we did the trial. That's 100 because we looked at 100 students. So the proportion of students with AB blood is 3%. So the probability of having AB blood is approximately 0.03. This would be considered an unusual event because the probability of it is less than 5%, so it's unusual. And we know that having AB blood is rare. So let's look at the classical method. Well, this method applies to situations where we know all the possible outcomes, and all the possible outcomes have the same probability. In other words, these are called equally likely outcomes. So things like flipping a fair coin, choosing one student out of 250 in a simple random sample, all are equally likely. We learned that in Chapter 8 and 9. Very important. Because all of the outcomes are equally likely, then each outcome occurs with the probability of 1 over n, where n is the number of possible outcomes. So this time we can say the probability of E does equal, not approximately equals, but does equal the number of ways the particular event we're looking at occurs divided by the number of possible outcomes. So let's say that there are n equally likely outcomes. That means that the sample space has n things in it. And that's what you see in parentheses, the n parentheses s, n parentheses, equaling n. That's just a notation of saying the number in your sample space is n, and the number in your event, the number of events is m, so the probability is m over n. Now computing, we'll have to find out how many are in our event, and even in our sample space. And these are essentially counting methods, combinatorics, and it can be sometimes quite complex to figure these out. But let's look at a nice simple example. We're going to roll a die. The sample space for that, we know if it's a 6-sided die, it's going to be 1, 2, 3, 4, 5, or 6. So the number in our sample space is 6. Let's look at the event rolling an even number. Well, the only even numbers on a 6-sided die are 2, 4, and 6. So the number of ways we can see event E is 3. So what's our probability of event E? Well, the number of ways we see E, which is 3, divided by the number in our sample space, which is 6. So the probability of E is 3/6, or we could say 1/2 or 0.5. So we're going to learn a way to get our sample space and to look at an event. So let's look at this particular example. 3 students want to go to a concert, but there's only 2 tickets. 2 of the 3 are selected at random. So in other words, making a random selection. So each of these are likely to get picked. So if we put their names in a hat and we picked out 2 of them. So how could we find the probability that Catherine goes? Because the 3 students are Catherine, Michael, and Dana. Well, first we have to figure out what our sample space is. So here's one way, using a tree diagram to get our complete sample space. For our first pick, Anyone, Catherine, Michael, or Dana, could be picked for the first ticket. So we're beginning to find out what our sample space could be. Now, on our second ticket being picked, Catherine, if Catherine was the first one picked, then Michael or Dana could be picked for the second. If Michael were picked, then Catherine and Dana could be picked for the second ticket. And if Dana had been the first one picked on the first one, Catherine or Michael could have been picked. So our sample space is at that very end. You read off the branches. You go from the start, you see Catherine and Michael. That's one way. That's one set of people that could have went. Catherine and Dana. Then it could have been Michael or Catherine, Michael or Dana, Dana or Catherine, Dana and Michael. So our sample space has 6 different ways that 2 people could have been picked for these tickets. So how many ways were Catherine picked? Well, let's look. The very first one, Catherine or Michael. The second one, Catherine or Dana. The third one, Michael or Catherine. And then just second to last, we see Dana or Catherine. So there's 4 ways Catherine could have went out of the 6 possible outcomes. All of those 6, again, equally likely to occur. 4 out of the 6, Catherine must go. So now we're going to talk about probability models. What's a probability model? Well, it's a mathematical description of long-run regularity consisting of a sample space and a way of assigning probabilities to the events. Now, we've studied one of these back in Chapter 3. It was a continuous probability model, the normal distribution. We studied the standard normal distribution and showed how any normal distribution, how it could be brought to the standard normal, and we used Table A. So that was a mathematical model we used to describe a continuous random variable, and that continuous random variable having certain characteristics. Now we're going to learn about discrete and one other continuous, but there are many continuous and many discrete. We're just going to look at a couple. Well, several. Well, let's look at this example, the probability model for 2 dice. We roll a pair of fair dice, and this is the possible sample space that could happen. Rolling a 1 with the 1 die, a 1 on the second. So we have 36 possible outcomes, each equally likely. So each one of these that we see here has a 1 in 36 chance of occurring. And we could have a sample space. This is our sample space. Now our model for this, we could say our random variable is the number of dots we read after we roll the die. So that's our random variable. We'll call it x. So our x can take on values between 2 and 12. So we literally count the dots on the 2 rolls. The smallest number we could get would be 2, because the smallest number on each die would be 1, so the smallest number we could get was 2. And since 6 is the largest number on each die, 12 would be the largest number we could get. So our random variable will take on values between 2 and 12. And now we can actually talk about the probabilities of these. The probability of rolling a 2, well, there's only one way that we could do that. There are 2 ways that we could roll a 3. You can see that there are 3 ways to roll a 4, and so forth. So here is our model. And so we have a probability model, and we can answer different questions using this.